Ok, estamos al aire nuevamente. Aprovecho de darles y saludarlos, darles las buenas tardes en Chile. Esta es la última sesión, de la novena sesión de las conferencias que hemos realizado con motivo de la celebración del mes de la Aeronáutica y el Espacio que organiza el Colegio Ingenieros a través de la especialidad nuestra. Estamos en vivo y por lo tanto las conferencias van a quedar grabadas. Hay una posibilidad de preguntas y respuestas abajo para que quienes quieran hacer algo durante la exposición lo hagan y al final vamos a poner las preguntas. La exposición dura alrededor de 45 minutos, máximo una hora, y debido a que nuestro expositor de hoy día es inglés, la transmisión va a ser en ese idioma y por lo tanto me van a disculpar ahora, tengo que pasar al idioma inglés. Well, first of all, Mr. Alan Thomson, thank you very much for your time. I will introduce you some words because Mr. Thompson is an experienced high-profile communication and government affairs executive with diverse multinational experiences, specialized in international trade development, market access, development of legislation, and regulatory engagement, supporting the space industry development in the UK. He currently is head of the government affairs in Skyrora, supporting the launch vehicle manufacturer to achieve its ambition of providing regular access to space. Launching from the UK, Alan is responsible for managing and engaging with all the stakeholders across the industry and government. This includes Skyrora's involvement in parliamentary space committees, industry associations such as UK Space, Scottish Space, Space Leadership Council, and others, and direct engagement with all government authorities, including the space flight regulators, UKSA and CAA. Well, I give you the floor to Alan to present his topic titled Skyrora, a small launch vehicle manufacturer and launcher, the journey to commercial launch in the United Kingdom. So again, thank you very much. And you have the floor, Alan.
Hello, and thank you very much for the invitation to share this small brief presentation with you. Lo siento, mi español no es muy bueno, but I hope you can see my presentation. As mentioned, the presentation is about the journey to hopefully commercial launch and about this company called Skyrora, which I'm here to represent. Before I go into the detail of the journey, I would like to share three key takeaways about the company that I represent. Skyrora is positioning itself as what is called sovereign assured responsive access to space capability. This means we're trying to do this within the context of the United Kingdom. We want to do it in an assured way, a reliable way, or in a responsive way, responding to the needs of the customers who need to get into space in a short space of time, and providing this basically logistics service provision. So allowing to deliver satellites into space, the access to space capability. This is what we like to talk about as ourselves. In the second instance, we like to say that we as a company are taking a step-by-step learning approach. This means that we are trying to engage with stakeholders, with regulators, in particular with governments and with potential clients around our progress. And this step-by-step learning approach, you'll see more about it throughout this presentation. We have undertaken successful 6 suborbital launches from the United Kingdom and from other places in a self-contained mobile launch complex, what we call a spaceport in a box. We have built an operational test site for the engine test activity that we need to undertake. This is the largest commercial test site in the United Kingdom. And we've designed, developed, built, and are testing an orbital spaceflight engine with 2,000 seconds of runtime. This is part of the step-by-step approach. And above all, in this strategic context, we want to deliver on the national space strategy, demonstrating responsible environmental launch, a capability, building resilience and sustainability, and overall growing the space economy. So as I said, we see ourselves as the logistics service provider, being able to provide that access to space for the United Kingdom. So who is Skyrora? Skyrora is a new space enterprise that is specifically manufacturing launch vehicles designed to deliver satellites into low Earth orbit. We in the UK, I'm sure you're aware, we're lucky we have a large number of satellite manufacturers, and particularly in Scotland, which is where we're based and where I'm from, we have in Glasgow 3 or 4, maybe larger, satellite manufacturers who are deploying satellites, Earth observation satellites. At the moment, their challenge for them is to get these satellites into space in less than 2 years. So we as a company are looking to be able to provide services to help these satellites get into space from the United Kingdom. These satellites mostly are Earth observation satellites. They're capturing information about the UK, the environment, the climate, so all to do with Earth observation data. And this is the 60% of these small satellites that we're looking to launch. We, as I said, we set ourselves up looking very much to have a relationship with these satellite manufacturers and to be able to do this from the UK. We wanted to do this in a mobile and modular way. This is what we mean by also responsive. So doing it without too much heavy infrastructure, and doing it in a flexible way so that we could capture the inclinations for the satellites, on the whole, we're looking for sun-synchronous or polar orbits, which means launching north from the north of Scotland towards the Arctic and over, and the orbits will be from pole to pole, from the North Pole to the South Pole. And these are the specific orbits that the satellite manufacturers, we believe, require of us in our country. We are doing this, as I mentioned already, in a responsive way. We're doing this, we believe, in an environmentally aware way, a responsible way. We have developed a specific process for taking unrecyclable plastic waste and turning this back into kerosene fuel, an equivalent of rocket propulsion RP1. We call this EcoScene, and we use this together with high-test peroxide, which is our oxidizer, which means that actually we are burning less carbon emissions, and therefore there's less CO2 emissions in comparison to a normal launch or normal thrust from a normal engine, another space rocket engine. And we're doing this, we are building and printing our engines, our rocket engines, on a 3D printer using advanced manufacturing capabilities. So we are taking the powder and printing the engines. This is the tech disruptive side of our business. And we believe doing this all together, we will have a useful launch offering, which is both cost effective or relevant to a market price, and will allow us to scale in an easier way to do more rockets so that we can address the demand for small satellites. So I talked about the step-by-step approach. Skyrora, when we were founded in 2017, we came up with this idea of starting very small and trying to build and test. Through testing, through demonstrating launch, we could learn ourselves, build our heritage, and critically, as you can see here with the step-by-step approach, through small launch vehicles, we could take regulators or stakeholders with us on that journey, or potential investors, or indeed our customers. So by saying that we started small, we learnt the lessons of how we were going to launch a small launch vehicle. In 2018 to 2020, we had 3 demonstration flights of small launch vehicles. I've got some images and videos I can show you a bit later on after I've shared the main material with this about that activity. Most notably, we moved on from that to a 2-stage vehicle called the Skylark Micro, and we did a demonstration flight in 2020. Actually, we ended up doing that demonstration flight in Iceland, mostly because of the remote nature of Iceland as a country, and it being nearby. When we're looking towards more regular orbital launch from the United Kingdom, Iceland is a country that we need to have involved, or at least aware of what that is. So that's why we went to Iceland to undertake a small test launch of a 2-stage vehicle. Then more recently, in October 2022, we developed our main suborbital launch vehicle. Again, I'll give you more details about that in a minute. And we undertook a launch of that, and I can share a video about that as well. This is, again, a vehicle which basically has all of the subsystems of our main launch vehicle on board, all of the capability that we need in our main launch vehicle. So we were testing out this capability, these subsystems on our smaller launch, our suborbital launch vehicle, so that by the time we get to readiness for a demonstration flight for our Skyrora XL, we hope that we will have exhausted all of the potential obstacles or challenges, so we know we know what could go wrong, and we can better manage it so it doesn't go wrong, if that makes sense. So that's the idea behind the de-risking approach to launch. And as I said, we're waiting for a launch license in the United Kingdom from the regulator, the Civil Aviation Authority. We expect to receive that license in December for us to be able to do a second test launch of the Skylark L, of our suborbital launch vehicle, hopefully in the first half of next year. And
Okay,
that will
Alan,
be our first. Yes.
I want to take 1 minute, because they are asking if you can put the full presentation, the screen.
You can't see. Oh, I'm sorry.
Yeah.
Just a second.
Yeah. If you can go full presentation, just like that.
Apologies. Is that now the full presentation? Can you see that?
Okay, yes, great. Very good. Thank
My
you.
apologies. I'm sorry. I think
no
in any
problem.
case, we're sharing a copy of this with you so
Yeah,
that you can have a look
absolutely.
at it in
All
PDF
right.
form afterwards. But yes, so these are the details, but I haven't got into any technical details yet. This is just the general direction of travel of the company. This is the orbital launch vehicle that we're developing, which is a 3-stage launch vehicle. We like to talk about Skyrora XL as the taxi service to space. We're not pretending to be the big bus that Elon Musk has developed. We are looking to provide a service which includes the last mile, so delivering the satellites to their specific orbit, and being able to support those satellites in orbit. And what allows us to talk about that is our third stage kick stage, or orbital transfer vehicle. This is again a slightly smaller propulsion system. Again, I'll show you a bit more about the propulsion systems a wee bit later on. But this is a 3.5 kilonewton engine on board this third stage, which allows us to talk about in-space support for the satellites that we're going to be delivering into space. The main thrust block of the engine in the first stage. The engines, we have 9 70 kilonewton engines on the main thrust block. Essentially, the first stage, as you can see, is a great big fuel tank. We are looking at what's known as coaxial fuel tanks. So we have there's an inner fuel tank, which you can probably see on the design here. The inner fuel tank is the kerosene tank, or the rocket propulsion RP1 fuel tank, and the outer, going around the entire diameter of the body of the engine of the rocket, is the peroxide tank. This gives us an approximate ratio of 6 parts of peroxide to 1 part of kerosene, and that's exactly what we utilize for our thrust in the 70 kilonewton engines. On the second stage, again, we have a coaxial fuel tank, and we have a 170 kilonewton engine. So in total, we have 10 70 kilonewton engines for one launch vehicle, plus one 3.5 kilonewton, which is for our orbital transfer vehicle. Why are we trying to master this concept? Because, as again, I'm sure you're aware, the bus service is all about price per kilogram, or price per dollar per kilogram, and how we can reduce that. This service, if we're going to say we're a taxi service, we're trying to look at, again, providing more of a bespoke service to our satellite users. In fact, if we can pivot towards the in-space support for our users, we can start talking about constellation management services. And so that we provide this logistics service as a service to satellite operators. So, for example, we can talk about supporting a constellation of 90 or thereabouts satellites in space. We can talk about if one of the satellites was to go out to have a malfunction, we can deploy replacement satellites on the launch vehicle on the top of the third stage. The third stage would deliver them to the orbit. The third stage then could have a capability to maneuver these satellites in space, so you can move them from one orbit to another, or we could have the capability of refueling those satellites in space, or other typical mechanical errors that the satellites could develop. We could address some of those with a capability on board the third stage. And ultimately, the third stage, we're looking to remove these satellites at the end of life. So we're providing a kind of like a debris removal service, or a service for, again, design to demise, because, as I'm sure you're aware at the moment, a lot of people, there is concern about the buildup of debris in low Earth orbit, in geostationary orbits, and this is something that we believe will allow us to not just talk about deploying satellites for the first time, but actually it will make us a sustainable service provider going forward, as we said, whether that's for constellation management services or for exclusively addressing the issue of space debris going forward. So this is the very convenient design of our launch vehicle that we believe will allow us to continue experiencing demand for at least the next 5 to 10 years and thereafter. As I said, we mentioned a little bit about eco-friendly launch, the idea of this peroxide and kerosene mix. The interesting thing is this is a quintessentially British technology that was, you're probably aware, it was deployed on the Black Arrow launch vehicle in the 1970s, when the UK last had what you could call a sovereign launch. It was a vehicle that was developed, designed and built in the UK. It was launched from Australia in October 1971, and this utilized this peroxide and kerosene mix. The interesting thing about peroxide and kerosene, when you're burning it, you probably know, is the specific impulse is not as high as liquid oxygen and kerosene mix. Therefore, the takeoff is much smoother. It's like a limousine taking off, which actually allows us to talk about a less G-loading on the payload during takeoff. So there's less shaking. It's a smoother launch, which means we could potentially talk about better, more sensitive optical satellites that we could take with us and give them an advantage of less shaking on the way up. But yeah, these are some of the features of our main service offering going forward. We have manufactured a prototype of the third stage. We've done a fire testing in a vacuum of that engine. We've looked at, we understand that this third stage can start and stop in space for up to 2,000 times. So we could have 2,000 individual missions, or whatever that could mean. We have developed a second stage prototype of the second stage, and we have done a vertical fire testing of that second stage. And we're currently in the process of manufacturing the first stage, which is this very long, it's about 11 meters long fuel tank. We have, as I mentioned, we're testing our engines on a regular basis, and again, there's a bit more information about that. But as I said, the idea that this design of rocket, we believe, will allow us to be sustainable, going through the excitement around launch and delivering things for the first time, but also supporting them in space going forward. The third stage, the orbital transfer vehicle, or space tug as we call it, this is an image representation of what we're looking to do. This actually is the top left-hand corner is the second stage plus the third stage plus the payload on the top. Here you can see we have designed the third stage, or we have a design with satellite, solar panels to provide some additional power source to the third stage. And here we have, again, a feature which is obviously a robotic arm to help us capture and connect with the satellites, whether that's to refuel them or to maneuver them around. As I said, in the first instance, the idea for this orbital transfer vehicle is to provide support. We talk about correcting the satellite or spacecraft orbit. We talk about deorbiting space debris, refueling satellites. It could actually, this third stage could be very much seen as an autonomous spacecraft, and the possibility around doing things with lunar orbits or interplanetary missions. And of course, then we're looking at the military applications, the potential for that going forward. So that's the main offering, but where have we got to so far? As I mentioned, we went and we did a test launch of this vehicle, the Skylark L, a suborbital launch vehicle, 11.5 meters long. As you can see there, it's deployed on the back of a lorry, a truck, a trailer. And this was actually in Iceland in October 2022. Because we have been waiting and negotiating with the UK regulatory authorities for a long time, we actually continued our relationship with Iceland and found an opportunity within Iceland to negotiate the possibility of undertaking this launch. And it was me who persuaded the Icelandic authorities to walk through a process to give us a certification or a certificate or a permission specifically to undertake this activity. So we were lucky. We had the chance to do this, and this is what we undertook in 2022. We wanted to demonstrate the capability of this launch vehicle. This launch vehicle actually is a pressure-fed vessel. So the propulsion system is a 3-ton engine or 30 kilonewton engine, which is pressure fed. In fact, if you look at the structure of this vehicle, you can see the pressure tanks themselves. So the first black stage is the kerosene tank. The second stage is the peroxide tank. And up at the top here, we have a helium tank, which we're using to pressurize and force the peroxide from the tank into the engine. As again, I'm sure you're probably aware, when you force peroxide H2O2 under pressure through a catalytic converter, it decomposes and you achieve very hot oxygen in its pure form. The oxygen is about 600 degrees Celsius, which when you mix it with kerosene naturally combusts. So you don't need a spark or an ignition spark to allow the combustion process to take place. And it's this that we're relying upon in this vessel, in this launch vehicle here, the pressurized peroxide, which allows the vehicle to leave the pad. In the event, the attempt for us to undergo that launch was not as successful as we'd have liked. It did leave the pad, but we had some challenges, some issues with the command and control software and the communication with the launch vehicle, so that the video that I'll show you later of this, you'll see the peroxide turning into very hot oxygen, but the kerosene didn't come in for a while. And then eventually, when we pushed the button to abort the mission, the kerosene came into the chamber, and the vehicle did actually leave the pad, but then very shortly thereafter aborted, and the launch vehicle then it broke up in midair and splashed down in the ocean. So it wasn't a success in terms of going to the 126 kilometers apogee that we had planned. And this is the other reason for us wanting to undertake this launch attempt again, as I said, hopefully in the first half of next year. But again, I'll show you a bit more detail in terms of the videos about that activity a bit later on. So Skyrora, as you can see here, this is our launch, our vehicle assembly plant just outside of Glasgow in Scotland. This is where most of the assembly and the engines are printed, and the fuel tanks are being manufactured at the moment. This is still very much R&D, so we're in research and development stage where we are looking to move towards scaling very soon, but we have as you can see from the suborbital launch vehicle, we've passed critical design review. We're now at a stage where we're into almost regular exploitation, and trying to achieve that TRL, the technological readiness level 9, so we can prove it through an effective spaceflight. But the main tanks of the first of the Skyrora XL are being manufactured in our facility up here. And yeah, an image of the engine test site that I mentioned earlier on. We have developed our own engine test site and systems. Here you can see on this, you can see one stool, which is a tripod stool for the 30 kilonewton engine. Again, very quite light. And actually the second sort of A-frame here is for our 70 kilonewton engine, where we have most of our engine tests. Today, we have on average an engine test a week to be able to prove 10 engines for our main go-to-market vehicle. This activity, as I said, we have at least a test a week. We put the engine up, we test it, we take it down, we take it to bits, we reassemble it and put it back up. And this is what the engine test activity looks like on the left-hand side here. But yeah, you can see very much in our approach to this testing activity, we're doing this utilizing shipping containers. So we're trying to be as mobile and responsive as possible without too much significant heavy infrastructure or changes to the environment. Here we've basically created a concrete pad, which is what the infrastructure here, and essentially behind this infrastructure we have some pressurization, again very similar pressure vessels. We do have additional infrastructure around a flame deflector and a water pit, basically to capture all the water that's coming over the flame deflector, and water fire systems. But yeah, that's a very brief overview. And this is now a glimpse inside our facility, our manufacturing facility. Here you can see some of the payload fairing, the nose cone of the main go-to-market vehicle. Here you can see an image of our third stage, again the prototype that we've developed. And here on the right-hand side you can see some nose cones for the further Skylark L, the suborbital launch vehicle. So yes, what powers it? This obviously is a very key capability for us, and we're very proud of our engine development and our engine capability. Here again, you can see on the left-hand side an engine being tested at our test site. Our head of propulsion developed 3 engines in 5 years. He designed, developed, had them printed, and then has gone through to testing. As I said already, the 3.5 kilonewton engine has been designed mostly for in-space propulsion systems. We believe that having a 3.5 kilonewton engine, peroxide kerosene based, actually, as we've demonstrated in our third stage or orbital transfer vehicle, is the right amount of thrust, or delta V, to allow us to support the satellites on orbit, and allow us to pivot towards that kind of different kind of economic model for us to provide our services to our customers. The second vehicle, the propulsion system here, you can see is that pressure-fed 30 kilonewton engine. Again, quite simple. It's very simplistic. You can see the combustion chamber here with the catalytic converter above it, and quite literally the peroxide gets forced in and combusts naturally. And the 70 kilonewton engine, which is obviously quite complex by comparison to the 30 kilonewton, essentially it's very similar in size, but you have a turbo pump here, which relieves us of the necessity to make the pressure in the pressure vessels quite so significant. With the turbo pump, we can achieve the same pressure and they get a better pressure. In fact, this 70 kilonewton engine, while we declare it nominal propulsion of 70 kilonewtons, we're actually in the process of trying to understand if we can get 100 kilonewtons out of it. Because of the tests that we've undertaken, we've been through 9 engine tests with each of those with 9 engines, and we've now taken one of the engines a bit further, and we're still pushing that envelope. but we've achieved engine qualification for those 8 engines so far. The propulsion systems, as I mentioned, are 3D printed. We have developed our own 3D printer. This is the main image on the right-hand side here of this system. It is 5 meters wide by 7 meters long. It's quite a large system, as you probably can guess, by the printable area, which you can see here. We have a direct energy deposition head on this part, and that's what does the printing. So we're actually doing the additive manufacturing. We also have a subtractive head, which allows us, so without taking the item that we printed off the bed, we can replace with the subtractive head, so we can actually do the post machining. We can finish the item on the same device, and saves a huge amount of time. So we can print, finish, several iterations of this, and this allows us to speed up the manufacturing of the engines. We're really hoping to be able to manufacture a whole engine system, the 70 kilonewton one, in about a week, which is what we're looking to achieve. But we probably need, to be able to do an engine a week, we probably need at least 2 or 3 of these large printers to be able to do that. But this is our own design, this is our own capability in-house. And as you can see, it allows us a huge cost saving on the traditional engine manufacturing that's been taking place up until now, which is why we have this capability in-house. Again, another image of the test site that we're very proud of, because this was a development that we found this quarry. We are leasing the quarry, and we've invested, I think it was a total amount of £1.5 million into the development of this, so that we can undertake this engine test activity. We received the European Space Agency money to allow us to do that, but the fundamental thing from our point of view, it gives us the opportunity to test whenever we want. We're not reliant upon anyone else, and this is quite a remote facility. There aren't any houses nearby, so there is very little pollution, noise pollution, and as you probably know from the chemical propulsion systems, there's when a peroxide combusts, we end up with steam essentially, and very little carbon dioxide emissions. So yeah, this is a key capability for us, and something that we've obviously invested into to allow us to do this quicker. I mentioned, we talked about a spaceport in a box. In Iceland, we took the vehicle there, you can see at the bottom right hand corner, which fits into the back of a trailer. And we took all the other containers with us, with the command center, the oxidizer filling, the fuel filling systems, the compressed gas supply systems, mobile power station units. The image on the left-hand side is SpaceX in a very early days on the Marshall Islands, again demonstrating this cherry picker. This is the approach we're very much keen to stay with, which is very reactionary, low cost, and very, very responsive as far as we can see. In total, our mobile spaceport, we need 11 containers, which is what we shipped to Iceland to be able to undertake the launch that we did in October 2022. And this is just a geography of the potential launch sites that we're looking at to be able to launch north to achieve those sun-synchronous polar orbits. Here you can see our launch site of choice. This is the Shetland Isles, the most northerly part of the United Kingdom. This spaceport is Saxavord. This is again, from our point of view, it gives us the most clearest access to the Arctic, and without too much other human intervention. So there is actually a flight corridor between Iceland and Norway, and there is a gas pipeline. But apart from that, there's not that too much other human infrastructure which we would be interfering with when we're launching. From the northeast of Iceland, Tórshavn, where we undertook that suborbital test, there is quite literally no infrastructure above into the Arctic. So that makes it slightly easier from the point of view of getting airspace clearance and other things. And it's, as we said, it's very remote from the point of view of so very few other people incidentally around. But to give you an idea, the other spaceports in Europe, there's Andøya from Norway, who's very much a military rocket range in former life, which has now started to be a commercial spaceport, and the Swedish S-range spaceport at the top of Sweden there. Again, a relatively new development from formerly a military range. The German Offshore Spaceport Alliance is actually a sea-based platform, so it's a ship, and they're planning to launch from the middle of the North Sea. It may not happen there in the longer run because of the nature of congestion of the airways around the North Sea. So this is something that's still being projected and still being negotiated. In Scotland, there are two other spaceports or spaceport projects. One of them is Spaceport 1, which is on the western, the Outer Hebrides, the Western Isles of Scotland. Those of you with a defence understanding probably know that there's a massive, big defence danger zone around the west of the Western Hebrides. This is where military war games take place on a regular basis, and that's what makes it potentially suitable for having a spaceport in that area. And Sutherland is on the mainland of Scotland. This is a project being pursued by a company called Orbex, again, hoping to be able to launch with their own spaceport. But yeah, they're currently both in development. Saxe-Voord has already built a couple of pads, and Saxe-Voord is where Skyrora is planning to launch from in the first half of next year. This gives you a brief overview of the competitive landscape, who we think we are competing with. I mentioned just their company called Orbex. They are also resident in Scotland. They're the only other launch vehicle manufacturer based in the United Kingdom. They have a facility in Copenhagen, in Denmark as well. But essentially they are a British launch vehicle manufacturer. You may have come across PLD Space with the Miura. They have undertaken a successful suborbital launch from Spain, and we understand that they're now looking at other options for growing their launch service capability into a regular orbital launcher. Rocket Lab, I'm sure you will have heard of, in terms of a regular launcher. They're launching from New Zealand. And yeah, this is to give you an idea of a comparison where we sit. There are two other European launchers who we are very much competing with. One of them is called ISAR Aerospace. They are looking to launch from Norway, and they are a German manufacturer, essentially trying to take the German approach to automobile manufacturing and putting it into space. And Rocket Factory Augsburg, which again is a German-based manufacturer. And this is just for record to give you a comparator against Arianespace, where we see ourselves with the Vega launcher and SpaceX with the Falcon 9. But yeah, just to get an understanding and how we're trying to position ourselves, not just on the price per kilogram, but on this bespoke service. Because when we get to the ability to launch on a regular basis, what SpaceX doesn't have is this third stage inbuilt, which we sense is going to be the next stage of space development. I mentioned a little bit earlier on this idea of Ecosene taking unrecyclable plastic waste and turning it into a kerosene equivalent, a rocket propulsion 1 equivalent. We've actually done it in a way where we can basically fit the entire infrastructure needed into containers. So yes, we can make it mobile. So yes, we took it with us to Iceland, where we took a large amount of the plastic waste on the beaches and recycled it in using the pyrolysis system and turned it into our Ecosene fuel. So this is actually quite an interesting device to allow us to be mobile from the point of view of fuel. We take unrecyclable plastic waste and turn it back into rocket fuel. And on the peroxide side of things, we're also taking undiluted peroxide with us, and then we can dilute it in our we have a distillery that we've got in a box. Obviously we're Scots, we like distilling, we like whiskey, so we have a distillery with us wherever we go. But yeah, this is what makes us mobile as a capability. And this is just a reflection of our younger staff, the idea we are inspiring new people to try and come into rocketry and engage with us in that. Some of our social responsibility and particularly the rocketry commands. The UK SEDS is the United Kingdom Student Rocketry and Space Exploration and Development Society. And we have here as well, we're interacting with the the students at universities who are interested in the rocketry clubs. So yeah, that's basically an overview of the company. These are the three key takeaways that I started with in terms of who we are and what we're doing. We believe we have this opportunity to be a sovereign, assured, responsive access to space. And we're doing it, as we said, in a step-by-step way. We hope to be able to launch our main go-to-market vehicle from the United Kingdom by 2026, and then go into regular commercial launch. And that is the overview of the company. If I do have some time left, I can show you some videos of some of our activity. Or what would you like? Would you like me to answer some questions? How would you like?
Oh, okay. You can show if you have some videos. We have time.
Sure. So this was one of the first small launches that we did from, in fact, the north of Scotland. And I'm gonna apologize. I think I'll try and take the sound so it doesn't deafen people. But yeah, this shows you the small launch rail with the very small launch vehicle that's 1.5 meters long. But this again allowed us to understand the safety procedures around launching. It was a solid rocket engine that we launched there, and it went to an altitude of about 5 kilometers. Sorry, yeah, it was 5 kilometers. Yes, so not very high. We had GoPros on board, and we had some nice video images from doing that. The second launch I mentioned was the two-stage launch from Iceland with the micro, what we called it, and this is a brief video of that activity. Sorry. Again, in a very remote part of Iceland, you can see. In fact, it was we did have a group of locals watching us, and this was the command station where we pushed the button. And demonstrating the capability of a two-stage, so the separation of the launch vehicle in space, and the first stage of the vehicle continuing on after the main second stage had expended. We achieved 26 kilometers with that launch, and we demonstrated some deficiencies of Iceland, particularly around the GPS tracking. This was the static fire test we undertook of our suborbital launch vehicle back in 2020. This was to demonstrate the capability of the launch vehicle ready to launch. So this was a firing of that vehicle as if it were going through launch. And you can see there we're holding it down so it doesn't take off, because we didn't have the permission to go into airspace at the time, and we didn't have the license. But this was just to demonstrate that we're ready to go to launch. This was back in 2020. As I said, we're still waiting to undertake that launch from the UK even today for our main license. And this is a couple of more images about our activity in Iceland and the Icelandic launch attempt that we undertook, which, as I said, was unfortunately not successful. But hopefully you can also see this again. What a great country, very remote, and this is our idea of demonstrating the mobile launch complex, challenging ourselves to find a field, a remote place, and launch from a field. And here you can see the mobile launch complex, the setup being put down with the containers, preparing the site. Here you can see that again the launch vehicle on effectively the pad, but the pad in this instance was a metal sheet of metal, and we launched it from, or rather we set it up to be able to launch from there. We had a bit of a challenge in terms of the weather, because this was October, so the wind, it was very, very windy. We had one of the biggest storms in that part of the world the day before we actually launched. And of course, in this instance, it was the storm and then the calm after the storm that we launched. But it was quite cold as well, so it was freezing, and we had some challenges around that. But here you can see the peroxide going into the engine and being forced down. We didn't, and that's the point when the kerosene hit, and it did leave the pad, as you can see, but we didn't have a nominal flight, as we mentioned already. So that was part of that. This was, again, some of the challenges of that, and the excitement in Iceland of the road being washed away in some extreme weather just before we started our launch attempt. This is a quick video of the third stage, the orbital transfer vehicle test that we did back in 2020, in December 2020. Again, a mobile setup where we took the 3.5 kilonewton engine and the orbital transfer vehicle. This is the prototype that we developed. Here you can see the spherical fuel tank approach. They are with bladders, and the smaller spheres are for helium to allow us to pressurize and push the fuel into the combustion chamber of the engine. So yeah, that was to demonstrate the capability of the space tug, or the orbital transfer vehicle. And this is again a very quick reflection of our testing of our second stage of the main XL launch vehicle. This is something we did in when was it, August 2022, before going on to Iceland. This was again in Scotland at a former decommissioned airbase. Here you can see the 70 kilonewton engine with the full peroxide tank and kerosene tank inside, and this was us to demonstrate that capability. As you can see, we had a very successful test campaign. So this gives you a flavor of what we're looking to be able to achieve going forward. And this now is, again, a brief overview of some of the engine tests that we've undertaken at our engine test site. Again, this will give you a better understanding of how the engine burns, what we achieve in terms of the propulsion system, the ISP, how does it look, and what we're doing on a weekly basis at the moment. Here you can see the gas chamber and the propulsion, the turbo pump, and that now is the engine going at full power. So there's more of that, but I think I'll leave that for the moment. So these are some tests, some videos. How can I answer some questions?
Okay, thank you so much for the conference. Very comprehensive one, to have an idea of what you are doing. It's amazing, let's say, the advances that you made. And well, there are a lot of questions. So I will go over about the 3D manufacturing printing machine that you have. There is some kind of limitation to export those kind of machine because they are, let's say, very critical in the wrong hands.
So we've developed that printing capability ourselves. It's a laser direct energy deposition head. It's not ITAR controlled. Yes, well, as far as I'm aware, there aren't that many. So the limitations on the capability, the UK is not putting limitations on the capability as such. It's more around, well, yeah, there's this thing called Missile Technology Control Regime, MTCR, which is this an international convention which regulates the underlying capability or the actual end product. So, for example, when we went to Iceland, we had to achieve an export control license to allow us to take the launch vehicle to Iceland. What's being regulated in this instance, as you said, is the end user, the country itself, who's doing what with it. And this is actually for the launch vehicle. The 3D printer per se, I don't think is controlled. So as a capability, I know that sometimes the powders and the ability to get the powder to be able to print is controlled. But on the whole, I think it's become much more, where it's liberated, it's become much more easy to access, as far as I'm aware.
Okay, thank you. Hello, Alan. I appreciate your wonderful presentation, said Fernando. A question is any possibility to cooperate to launch in Southern Hemisphere countries like Chile?
We're very much open, as you can see from our approach to trying to achieve what we want to do, which is regular launch. We're very much open to discussions about how we can collaborate, not just in the UK or in the European geographies, but also outside of that. and also share some of our experience, maybe for the benefit to allow other nations to achieve regular commercial launch, if that's appropriate. So yes, delighted to be able to continue or have a discussion about what we can do and what might be possible.
Great. And you were launching in Iceland, which is about 65 degrees, but Australia is minus 35 and Norway is 60. So it does make any sense to go, let's say, to minus 53, or because from the orbital point of view, mechanical of orbit, it should be the best to be closer to the poles, less energy, I suppose. So, but you are trying to launch from UK, Brits, and Iceland. What is the game there? What is the, let's say, the conditions in order to launch, let's say, from UK and not from Iceland or Norway?
So yeah, the region for Saxavord was the most northerly part of the UK, and again, so in the first instance, the location of the spaceports for the UK was around remoteness and lack of other human infrastructure. The secondary point was, again, what the inclinations are available and the time to orbital insertion. So the satellites that we are looking at, again, are mostly looking at sun-synchronous or polar orbits. They're not geostationary, and while yes, because of the mechanics of the Earth, while it might be better and easier to launch to geostationary from the equator, our customers are not looking for that. They're looking for a quick time to orbital insertion over the North Pole, and for their satellites to be able to do a sun-synchronous orbit, which gives them the maximum coverage of Earth for observation or whatever else it is. So yeah, the advantage of having again a northern incline, the advantage of being able to launch from Shetland, as I said, is more around infrastructure. Same with Iceland and Norway. The further north you go, the less infrastructure and the less. So we hope to be able to get into orbital insertion over the Arctic, so that that's the kind of length of time that we want to be able to achieve that. And while we're over the Arctic, there is little other infrastructure that we are going to, our first stage when it comes splashing down, will not damage or incur into. So that's the kind of rationale for the northern, the kind of firing north from the north inclinations.
Oh, okay. And about what you mentioned about the satellite observation market, your goal is to take something about 60%. That goal is concerning the price or the cost of your launchers to be more competitive than the rest.
So I think the United Kingdom goal is to try to get, I think it was like 10% of the total space economy, which I think is also quite a high number. Now, I think we are, as I said, more in the area of being bespoke. We're looking, so I think 60% of our satellite customers are mostly at the moment Earth observation satellites. We are seeing telecommunication satellites, so Internet of Things or internet satellites, smaller versions of Starlink or very specific network satellites that need to be over a specific place. We are seeing some of them looking for specific inclinations. But yes, on the whole, we're looking to be, as I said, more on the responsive side of things. If we were to work with an internet service provider, it gives us the best commercial demonstration of our capability or the best value, because if you imagine your internet is happening in space and it's not working, and you can identify that one satellite is the error, the cause for that malfunction, we can then provide a responsive launch, a launch in a short space of time to deploy a replacement satellite, or we can talk about supporting the satellites in space to maneuver one to be able to cover it, or that's the kind of service we're looking very much more towards, which is again more focused about the pivot to in-space support rather than the actual deployment, as I mentioned.
And how has been the private sector as a partners with Skyrora? Because after all, you have to get money for the project from the state and from the private. How is that market is behaving now?
So yeah, I think it's a very good question because as I think you probably know, with Elon Musk's journey to regular launch, he got to a point where he was looking for, I think it was a 300 million investment, and he got close to putting the entire company on the line in SpaceX, which is exactly the kind of, that's the ruthlessness, the kind of faith that you have to have. From our point of view, for us to be able to achieve a, let's call it a market relevant solution. So we think that we need in total up to 150 million. This will allow us to undertake complete R&D and have not less than 3 launch vehicles ready to start a regular commercial launch service. Then we think it will take another 50 million to achieve scaling, which will allow us to go into a more regular service. But yeah, so we're talking about 200 million. At the moment, the company, Skyrora, has been funded by its founder. It's been very difficult to find private sources of financing to attract them because we've been going through this stage of R&D. It's been a protracted stage of R&D because, again, first of all, this is a new activity we've reintroduced to the market. No one really understands it. So a lot of people are having to relearn it. The idea we'd had around this de-risking launch and with these iterations and these steps, we thought was going to be a better approach for investors because you then demonstrate the value add. But to be honest with you, because of the lack of regulation and the lack of understanding, we found it that the first 7 years of this company have been very much what's known as a Hail Mary or a big risk. Now we've got to a stage in our development as a company where we are beginning to see commercial contracts coming into the company, whether that's for parts of 3D printed, so the ability to print something and sell it and realize it, or whether it's for subsystems and the propulsion systems. So being able to take these commercial contracts, we then have a commercially relevant offering to the market, and we can leverage that against future investment. So yes, the more market relevant we can make ourselves before we complete our journey on R&D, the better we can get better leveraged investment to come in. But it's an enormous challenge, and it's an enormous challenge in terms of sustainability of the service going forward. I think the example that people don't understand of Elon Musk is that actually, for a successful smaller launcher to be successful in Europe in particular, we expect 2/3 of the revenue needs to come from a government, and it's mostly from the defense side of things, where we expect the 1/3 to be from the purely commercial launch services opportunity. So yeah, there's without that, it's a very difficult activity to make sustainable. But yeah, that's the kind of idea that we think we have in our head.
Yeah, I have some minute for the last one, and the last one is regarding or concerning the regulation. What kind of recommendation you will give? Let's say in Chile, we are facing a long project to be in the space the next years. Build satellite. There is a roadmap about that. What kind of recommendation you will give to the local authorities or the people in charge concerning all kind of regulations that should be accomplished by the country?
So the problem that we've had is, as I said, is that the activity we've done, very few other people have been doing it. And the issue we've been trying to persuade the regulator is to learn alongside ourselves. That's why we took this de-risking approach to launch. Learning together, collaborative learning, and ultimately, because in a regulator, we need to see people who have our capability, who can help us measure the risk of the activity. If you don't understand the engineering of the original activity, it's very difficult to measure the risk. So the disparity in knowledge between industry and the regulator is the reason why it's taken so long for us so far. So if there's a chance, so from our point of view, we want to get, we would love to have a relationship with our regulator where we just spent all the time with them, teaching them about our systems, allowing them to understand it better and to become better qualified in understand and identifying what those risks are. We are now looking to do this through what we're calling regulatory sandboxes, where industry talks about our concept of operations, regulators sit, listen, and interrogate, and then hopefully we achieve a discretion. So rather than having a regulation, we say, okay, now show us how you're going to do it, and we can all learn from the activity. That for us is the best way to iterate and to achieve a relevant regulator who understands and is at the same level of progress as industry. That's the way we hope to try to get a better way forward. What we found in Iceland was the willingness to allow us to do it and to engage around it. So yeah, for us, it's all about the equality of education and the speed, how we can educate together.
Well, I hope we will keep together because we have to learn a lot about that. Well, we are just in the time for the next conference. I know that this day has been a very exhausting journey for you, and even though you took the time to be with us, so I really appreciate very, very much, and thank you so much to be with us, and I hope to have you by the next year as well. So thank you, Alan, for your time, and I hope you and the company all the success.
Thank you very much. It's a pleasure and an honor to be sharing this information with you, and I'm delighted to repeat it and to follow up on some of the questions. Thank you very much.
Okay. Thank you, Alan. Bye-bye.
Thank you.